Okay, so welcome back. And today, so far we've talked a lot about convex functions, convex sets, and we looked at a few algorithms for optimizing or unconstrained optimization of convex functions. Right. So we have a good handle. So suppose someone gives you a function on Rn and asks you to minimize it, you have at least an array of tools that you can use. All of these are variants of gradient descent or Newton's method. All right, so you know how to do that. But what we didn't discuss was what happens if you have constraints. Obviously, if I just directly run gradient descent, it's going to look for the global minimum, right, or unconstrained minimum. But when you have constraints, obviously gradient descent is not going to help, because how do you ensure that you're always within the constraint set? Towards the end of last class, I mentioned that one way to get around that is to use this projected gradient descent, where you run gradient descent, but at the end of each step, you see whether you are still inside the constraint set or not. If you're inside the constraint set, fine, no problem. If you're outside the constraint set, then you sort of go back into the constraint set. So you find the closest point within the constraint set to the current iterate, and that becomes your next iterate. All right, and you keep running this, and you can give some guarantees on how well this projected gradient descent will work. But the problem is, how do you find the closest point within the constraint set? That itself is another optimization problem. In certain cases, you can work it out by hand, but for general constraint set, that doesn't work. All right, but still, it is a tool, nevertheless, that you have at your disposal. All right, so today onwards, we'll explore constraint optimization in more detail. In fact, we'll look at it from an even slightly more broader perspective. So initially, I will not even assume that my optimization problem is convex. All right, so let's look at the following general framework. So I have an optimization problem, which is in this particular form. All right, recall that not every constrained optimization can be expressed in this particular form, but a very broad class can indeed be represented so. So I want to minimize some function f of x. I'm not, at the moment, I'm not making any assumptions on what this function is. It could be convex, it need not be convex, doesn't matter. And the constraints are represented in this functional form. So I have a bunch of inequality constraints which are represented. I have n inequality constraints and m equality constraints. Okay, so this is the framework, and I'll assume that these functions f and f1 through fn and h1 through hm, all of these have some common domain D. If I don't say anything, then it means that it's Euclidean space. Okay, almost always we'll assume that this domain D, this common domain D, is the Euclidean space Rn or Rd or whatever of appropriate dimension. The other assumption that I will make is that there exists a solution and it's equal to P star. Okay, so there is some x that satisfies all of these constraints, and the value of f of x at that particular point is equal to P star. That's the minimum value of f of x subject to these constraints. Okay, so as we've seen, the constraint set, the set of all points in the domain that satisfies these constraints. I'll also refer to this as the feasible set, or in some cases I'll refer to this as the primal feasible set, for reasons that will become clear soon. So the primal feasible set is, or the constraint set, is simply the set of all points in the domain. We will typically take this to be some, let's say, Rd, such that all of the constraints are satisfied. So fi of x is less than or equal to 0 for I between 1 and n, and hj of x is equal to 0 for j between 1 through m. Right? So I have n inequality constraints and m equality constraints. So this is the feasible set. Now if and recall that this is the objective function is f of x, right? So if f1 up to fn, the objective function as well as the functions that define the inequality constraints, if these are convex, so all of these are convex functions over D, and h1 through hm are affine, then the optimization problem is said to be convex. So a convex optimization problem is basically one where the objective function as well as the functions f1 through fn are convex and h1 through hm are all affine. Okay, so this is just setting up the terminology. So let me begin by asking the following question. So we have this p star, right, which is the minimum or the constrained minimum of f of x, right? Can we get upper and lower bounds, non-trivial upper and lower bounds? On the minimum value p star. All right, so you're presented these functions, you're given f of x, you're given f1 of x, h1 of x, and so on. The goal is to, even before I get to solving this optimization problem, can I come up with non-trivial upper and lower bounds? What is a way of, let's start with the easier one. How would I get an upper bound on p star? What would be one way of getting an upper bound on p star? P star is the minimum value of f of x subject to those constraints. Correct. You take any point in the feasible region, all right? So any such point is called a feasible point. You take any feasible point, plug it into f, you get an upper bound, right? Because any x that lies in the feasible set satisfies all of these constraints, and therefore f of x has to be greater than or equal to p star. So take any feasible x, that is, take any x that lies, so let me have some notation for this. I'll call this script f. So script f is the feasible set. So take any feasible x f of x is an upper bound. Okay, that's straightforward. What about lower bounds? Is there a way of getting a similar lower bound, sort of just take in something that's feasible in some sense and get an automatic lower bound for P star. At the face of it, it's not obvious how you can do that. All right, but the whole point of duality is this. So the idea behind duality is to set up another optimization problem such that any feasible point for this dual optimization problem gives you a lower bound on P star. Okay, so that's a high level approach. So I'll now, so I have this optimization problem which I don't know how to solve yet. What I'll do now is introduce more variables and look at an even more complicated looking optimization problem. So let's define the Lagrangian So the Lagrangian is going to be a function of three sets of vectors, so three vectors. One is x, the other is, I'll introduce new variables called lambda and nu. Okay, so I have the domain, the x belongs to some common domain D, and I'll have these vectors, these new variables. I have n inequality constraints and m equality constraints. So the Lagrangian is consists of it's a function of x, one set of variables lambda. So I have one variable for each inequality constraint and one variable for each equality constraint. Right, so this is in D, which is a subset of r to the little d, and lambda, there are n variables, but I'll take all of these to be non-negative. And I have these one variable for each of the equality constraint. Okay, so that's why the inequality constraints are special. They're different from the equality constraints. Okay, and that's one reason why I formulated this in this very specific form, just to keep things consistent. So I want the optimization problem to be set up in this sort of canonical form. All of the constraints should be described as, all the inequality constraints are of the form fi of x is less than or equal to 0, and all of the equality constraints are expressed in the form hj of x is equal to 0. Again, it's just so that I have notational convenience, and the Lagrangian can be defined in an appropriate fashion. Okay, so what is the Lagrangian? It's equal to f of x. If you look at it only purely as a function of x and the fi's, this is basically a linear combination of the objective function and the constraint functions. So this is f of x plus summation I equal to 1 to n fi of x times lambda I plus summation j equal to 1 to m nu j times hj of x. Right, so for each inequality constraint, I have one of these variables which are called Lagrange multipliers, and for each equality constraint I have one multiplier. So here lambda and nu, these are called the Lagrange multipliers. Okay, so far it's just a definition. Right. So with me so far, any questions? Yes. So it means that each lambda I should be greater than or equal to 0. Right? That's where this Lagrangian is defined. I mean, you can look at this as a function on Rd cross Rn cross Rm, no problem. But the our real interest is only within this specific subset. We, in a moment, we'll see why I want these lambda i's to be greater than or equal to 0.
So x is consistently a vector throughout?
X is consistently a vector. Yeah. Okay. Great. So now I'll define this new object called the Lagrange dual. Right? Recall that this was called the Lagrangian. L is called the Lagrangian. Question? The Lagrange dual G of is going to be a function only of the Lagrange multipliers. I'm going to somehow get rid of the x. This is equal to the infimum over all x in the domain. Typically, this is going to be Rd of the Lagrangian. Okay. So I'm getting the Lagrange dual by solving an unconstrained minimization problem. Okay, minimizing it over all of D. Typically, this is going to be Rd. Right, so think of this as minimizing over all of Rd. What does a dual mean? We'll get to that in a bit, and why it's useful at all, right? So let's explore the properties of G of lambda comma nu. All right. Now, so first let's consider any feasible x. Okay. So for any feasible x, what can you say about L of x lambda nu compared to P star? Is there some sort of a relationship between P star and L of x lambda nu? So recall that L of x lambda nu is f of x plus sum over I lambda I fi of x plus sum over j nu j hj of x. So for any feasible x and lambda which is entry wise greater than or equal to 0. So each lambda I is greater than or equal to 0.
What is the point of the last term?
Which term?
Mu of j times
Um, what do you mean? So the Lagrangian is defined over all x, right?
Isn't it always 0?
So again, if x is feasible,
Then
then this last point is 0. That's what I'm trying to come at. But this Lagrangian is defined not just over the constraint set, but over all of the domain, over all of Rd. Okay? And in particular, this minimization that I'm doing to get the Lagrange dual, it's over all of Rd, not just over the constraint set. That's something to be kept in mind. So originally I have a constrained optimization problem. This one is an unconstrained optimization problem. All right? So it's different. So the value that you get here is going to be different from P star. the one that you're actually looking for. But in any case, suppose that I have some feasible x and lambda is greater than or equal to 0. So if x is feasible, what can you say about this quantity? It's equal to 0, because if x is feasible, then it must satisfy all of the constraints. So each of these, each hj of x should be equal to 0. And what can you say about each fi of x? If it satisfies all of the constraints, then fi of x should be less than or equal to 0. Right? So this quantity is less than or equal to 0. By assumption, lambda I is greater than or equal to 0. So what can I say about this entire quantity over here? This is less than or equal to 0. Right? So in that case, what can I say about f of x plus this? It's going to be less than or equal to 0. Right? So this quantity, so firstly, let's do it step by step. This quantity is going to be less than or equal to f of x. Okay? So what can I say about the infimum? Again, this is for constrained minimization. So infimum over all x within the constraint set, L of x lambda nu. This is less than or equal to the infimum over all x that satisfies the constraints f of x, which is p star. Right? Are you with me so far? Right? So the constrained minimization of the Lagrangian, or the constrained minimum of the Lagrangian, is less than or equal to the constrained minimum of f of x. So what can you say about the unconstrained minimum of the Lagrangian? Infimum over all x in the domain. Yeah, so this minimization over here is over a larger set. So the infimum over D can only be smaller than the infimum overall over just f. Right? So this obviously has to be less than or equal to p star. And this holds true for every lambda greater than or equal to 0 and for every nu in Rn. Right? So for every lambda greater than or equal to 0 and for every nu in Rm, the Lagrange dual function is always going to give you a lower bound on p star. So if I had to get a lower bound on p star, one way is to somehow find this Lagrange dual function and then put in a feasible point. So in this case, it's feasible if lambda is greater than or equal to 0. That's the only constraint. Somehow I had a whole set of complicated constraints. Now I have perhaps simpler constraints. Okay? It doesn't mean that I've simplified the optimization problem in any way. All right? Again, this need not give me a solution to the actual optimization problem that I'm really interested in. But in any case, for as long as lambda is greater than or equal to 0, the Lagrange dual function is going to give me a lower bound on P star. It may be close to P star, it may be far away from P star, but in any case, it's always going to give me a lower bound on P star. And this is true irrespective of what kind of a function f is, or fi is, or fj or hj is. All right? No assumptions on convexity or continuity or differentiability have been made so far.
What exactly does it mean that this less than equals B star is true for all lambda and gamma or why is it true for all of them?
Again, right, so if as long as lambda is greater than or equal to 0, this quantity is negative. And for every nu in R, this quantity is 0 because x is feasible. Right? Okay, so again, let's go back. So this is the definition of the Lagrangian. Okay, it's just a linear combination of the objective function and the constraint functions. All right? So that's what I have over here. Now, let's pick any feasible x, any lambda greater than or equal to 0, and any nu in Rm. Okay, doesn't matter which one. Just pick your favorite x, lambda, and nu. All right. Since x is feasible, if I look at the Lagrangian, hj of x has to be equal to 0. So summation over all j, nu j hj of x has to be equal to 0. So this quantity is always 0 for any feasible x. Lambda I is greater than or equal to 0. But since x is feasible, fi of x has to be less than or equal to 0. Right? Again, it satisfies the constraints, therefore each of these has to be less than or equal to 0 by definition of the constraints. So this whole quantity is less than or equal to 0. Right? So this whole thing, this extra thing that I've added to the objective function is going to be less than or equal to 0 for every feasible x and every lambda greater than or equal to 0. Doesn't matter what you choose nu to be. Say any set of real values. All right. So this whole thing is less than or equal to f of x. All right. You agree with that? Okay. So we have that first. So therefore, since this is less than or equal to this, the minimum of this over some set, over set of all feasible points, has to be less than or equal to the minimum of the right hand side over feasible points. Because this inequality holds for all feasible points. It doesn't hold for any arbitrary x. It holds true only for feasible x. So only if x satisfies the constraints do you have this inequality. If x does not satisfy the constraints, then I don't guarantee that this inequality holds. Okay? So if x satisfies the constraints, then this holds. So if the minimum of the left hand side over all points that satisfy the constraints, or for all x, is less than or equal to the minimum of the right hand side over all feasible x. Right? That's exactly what I have over here. But the minimum of the right hand side over all feasible x is by definition p star. That's the constrained minimum. Right? So the minimum of L over all feasible x is less than or equal to p star. But instead of minimizing over f, if I minimize over a larger set, which is let's say all of Rd, then the left hand side can only be smaller. It can only get smaller. It can't get any bigger. So the minimum of the Lagrangian over all x has to be less than or equal to p star.
No, it can get larger because the constraints are not satisfied anymore.
Doesn't matter, right? I'm only, so you agree with me up to this point,
Yeah.
correct? the right hand side is still, I'm not minimizing the right hand, I'm not changing anything on the right hand side, right? The left hand side, this minimization is over f. So I have infimum x in f x lambda nu versus infimum of L. I'm keeping lambda and nu fixed. I'm not changing lambda and nu. Okay? For a given lambda and nu, what can you say about these two quantities? Which one is greater than which? Remember that f is some subset of D. Yeah?
I don't know, because if the constraints are not satisfied, the F by H,
Okay.
then those terms which you put less than 0, less than or equal to 0,
Okay.
might become greater than or equal to
Doesn't matter, right?
It's the information.
I'm looking at the infimum. I'm not interested for any arbitrary x, right? Only thing I'm trying to do is I want to know what happens to the minimum value.
Okay, got it.
That's it. It's not a pointwise inequality. Because this minimum, since it's over a smaller set, can only be larger than this particular minimum.
Okay, got it.
That's it.
So if you take the supremum over lambda and mu,
I'm sorry, can you repeat?
if you take the supremum over lambda and mu,
Correct. Just I'll come to that at this point. But is it okay up to this point? All right. What I've established so far is that for all lambda which is component wise greater than or equal to 0 and nu in Rm, g of lambda nu, the Lagrange dual function, is going to be less than or equal to p star. All right, so if I plug in any value of lambda and any value of nu, I'm going to get a lower bound on p star. So what's the way of getting the best possible or the closest lower bound? Yeah?
supremum over mu is fine, but lambda is again constrained.
Fine, that's okay. But if I look at the supremum over all lambda greater than or equal to 0 and nu in Rm, g of lambda nu, this is going to be less than or equal to p star. Right? So I'll give this some notation. I'll call this d star. Okay, and of course now I have another constrained optimization problem over here. I don't claim to have simplified my original problem. Okay, think of it as a different way of looking at the original problem itself for now. Okay, so this is what is called the dual optimization problem. In no way am I claiming that the dual optimization problem is easier to solve than the original optimization problem, which I'll call the primal optimization problem. Okay, but if I'm able to solve the dual optimization problem, then I get a lower bound on p star. That's the only point I'm trying to make now. All right. So I have this d star, which is the solution of the dual optimization problem, and p star, which is the solution of my primal or original optimization problem. And d star is less than or equal to p star. All right. This is something called weak duality. So because I say that one is the dual of the other, so weak duality holds because d star is less than or equal to p star. Remember, so far I made no assumptions on f or f1, f2, f3, fn or hj's. They could be arbitrary, they could be non-convex, non-differentiable, no problem. All right. As it turns out, if we impose more restrictions on these functions, then it is possible to have so-called strong duality. That is, d star could be equal to p star. I'll get to that. Just wait for a minute. But if this happens, then I say that this problem satisfies strong duality. Because I have these two optimization problems. One, the primal optimization problem, which is a constrained minimization problem. The other is the dual optimization problem, which is a constrained maximization problem. And if strong duality holds, then the minimum value of the primal optimization problem is equal to the maximum value of the dual optimization problem. The minimizer and maximizer could be very, very different. I don't say that there's any relationship between the two. But the minimum and the maximum values match. Okay, that's when we have strong duality. That is if strong duality holds. Okay. Now there are a bunch of different conditions, and there's a lot of work on when strong duality holds. All right. So all we can give are sets of sufficient conditions for strong duality to hold. So these restrictions or conditions under which strong duality holds are typically called constraint qualifications. Conditions when strong duality holds, or d star is equal to p star. And one such constraint qualification is what is called Slater's condition. So Slater's condition says the following. I mean, of course, it doesn't mean when d star, it doesn't guarantee that d star is equal to p star, but Slater's condition is that if there exists, basically there exists some x that is in the relative interior of the constraint set, such that all of the inequality constraints are satisfied with strict inequality. Okay? It's a technical condition. The claim is that, or the result is that if the primal optimization problem is convex, which means that the objective function and all of the inequality constraints are convex functions, and all the equality constraints are affine functions, and Slater's condition is satisfied. Then strong duality holds. So just convexity is not enough to guarantee strong duality. We need this additional technical condition. In many problems of interest, Slater's condition is satisfied. It's only in certain pathological cases that Slater's condition is not satisfied for convex optimization problems. Again, the thing to keep in mind is that these are sufficient conditions, that the problem is convex and Slater's condition is satisfied. We'll see examples of non-convex optimization problems where you have strong duality. All right. So now let's go back to the dual optimization problem. In some ways, this looks a bit simpler compared to the primal optimization problem because I don't have very complicated constraints. The constraint set is basically the non-negative orthant for lambda and all of Rm for mu. So hopefully I should be able to solve this easily, provided of course I can compute the Lagrange dual function. All right. And we'll see that this duality approach indeed helps, because in some cases you can even get closed form expressions or closed form solutions to the optimization problem using this approach of duality. Even though the actual primal optimization problem is complex, there are ways of getting closed form expressions. Yeah, and even if you can't get a closed form expression, you can numerically solve for the minimizer. And in fact, the approach that we will take is, in some sense, we'll jointly look at both the primal and the dual problem together. All right, not separately. In some sense, we'll try to jointly solve for the primal and the dual variables. Right? But any questions so far? And the main point is that in many cases, you can actually get closed form expressions for the Lagrange dual function, because after all, it's an unconstrained minimization problem. Right? So just to get a feel for all of this, let's look at a few examples. We'll start with an almost trivial example for which you can just say what the solution is. All right, so let's start with the following. So I want to minimize, say f of x is equal to x square. It's just a univariate minimization problem, such that subject to the constraint that x lies in the interval from a to b. What is the minimum value? Yeah?
Greater of apps A or apps B.
Greater, it will be a little careful.
Less.
It will be a little careful.
If A is less than 0, then 0, or if A is greater than 0,
mean,
0 then
if A is less than 0, what if A and B are both less than 0?
If 0 belongs to the interval, then it's 0.
Correct.
Otherwise, the minimum.
So if the sign of A and B are opposite, or if A is negative and B is positive, then the minimum is equal to 0. Otherwise, it's the minimum of A square and B square. Right? Again, I'm only interested in the minimum value. I don't care about what the minimizer is. Okay? So this is this is 0 if whatever a is less than 0, or less than or equal to 0, less than b, and it's equal to min of a square b square otherwise. Okay, let's set up the dual optimization problem. So first, what is the Lagrangian? How many? So even before that, let's bring this into standard form. All right, what is the standard form? Minimize x square. How do I express the constraints? Okay, x less than or equal to b. Again, this is not in standard form yet. It has to be of the form f1 of x less than or equal to 0, f2 of x less than or equal to 0, and so on. So x minus b is less than or equal to 0, and a minus x is less than or equal to 0. So there are two constraints. Again, it's very important to bring it down to standard form. Otherwise, if you don't and you try to find the Lagrangian and solve for the dual, you'll get something totally wrong. All right, the signs and the direction of the inequality is very important. Okay, so this is the primal optimization problem. Let me construct the Lagrangian. How many Lagrange multipliers do I need? 2. So lambda 1 and lambda 2. I have two inequality constraints. So this is equal to x square plus lambda 1 times x minus b plus lambda 2 times a minus x. Okay. And g of lambda 1, lambda 2 is the infimum over x in R of this particular quantity. So what is the minimum equal to? So firstly, the right hand side. What kind of a function is this? Is this function? Yeah? I can't hear you. Yeah, it is. It's a convex function, right? Because it's x square plus something times x plus some constant. All right, and what is the second derivative? What can you say about the second derivative of this particular function? It's greater than or equal to 0, so it is convex. Okay, so how will you solve for the unconstrained minimum of this convex function? Yeah, so you take the first derivative, set it equal to 0, right? Because again, right now, to find the Lagrange dual, all I have to do is solve this unconstrained optimization problem. What do you get? What is the minimizing x? So this x star is going to be equal to lambda 2 minus lambda 1 by 2. Okay. Let's plug this back into the function. What do you get? What is g of lambda 1, lambda 2? Minus of
lambda 1 minus lambda 2 square
lambda
by
1
4
minus lambda 2 whole square by 4
minus b lambda 1 plus a lambda 2.
minus b lambda 1 plus e lambda 2. Did everybody get this?
Even if the dual optimization problem is non-convex,
So, okay, in this case, what can you say about the primal optimization problem? It's convex, right? Because the objective function is convex. The constraint functions are all basically affine functions, right? So, and therefore they're convex. Okay, so the primal optimization problem was convex. What can you say about the dual optimization problem, which is maximize g of lambda 1, lambda 2 subject to the constraint that lambda 1 is greater than or equal to 0 and lambda 2 is greater than or equal to 0. What can you say about this particular objective function? Yeah? So the object.
can make it convex.
So g of, what do you mean can make it convex? So this objective function g, which is equal to this, what kind of a function is it?
Concave. So you do something like minimize.
Doesn't matter. So it's a maximization problem, remember? Yeah. So it's maximizing a concave function, which is a convex optimization. Of course, the constraints are also basically linear. And
Quadratic cone, which you have mentioned on the lectures.
in which
Because that guy is a quadratic in lambda 1, lambda 2.
agreed, this is quadratic in lambda 1, lambda 2.
So you can express it in one of those A transpose X, X transpose A, X kind of forms.
Yep.
And this guy, the constraint set, is a cone.
It is a cone, I agree. It's just the first quadrant.
Yeah. So
Correct.
it's, I remember you had mentioned that quadratic cone optimization.
That was in a different context, perhaps. It was a quadratically constrained quadratic program, if that is what you are referring to. But this is not even a quadratic constraint,
Yeah,
it's
this
just
is
a linear constraint. But in any case, this is still a convex optimization problem. Okay. So I'll get to convexity for more general cases in a little bit, but at least in this example, we see that the primal optimization problem is convex, the dual optimization problem is also convex. Okay. And now let's try to sort of numerically verify whether duality holds, weak duality and strong duality hold or not. So I've written up a little program that just plots these things. So remember that the primal optimization problem, that's a function of just one variable x, correct? Whereas the dual optimization problem now has two variables. So in some sense, I've complicated the original problem, all right? But so I can plot this g of lambda 1, lambda 2 and compare the value to the minimum p star. I know that p star is equal to whatever, it's equal to 0 if a is, the signs of a and b are different, and it's equal to the minimum of a square and b square if both a and b are positive or both a and b are negative. Correct? So let's take a look at some numerical examples. So say a is equal to 1 and b is equal to 3. What is the minimum value equal to for the primal optimization problem? 1. All right. And I'll also plot g of lambda 1, lambda 2 for this particular a and b. So the blue surface that you see, it's just a flat plane. It's a flat plane with z-axis at 1, which is P star. Right, so this is 1. The blue line is basically at 1, and the brown colored surface is essentially G of lambda 1 lambda 2. And you see that this G of lambda 1 lambda 2 is always less than or equal to P star. So the level of the blue surface is basically at P star. So this brown surface is always below the blue surface. Right? So in some sense, at least weak duality holds. But then if you also observe carefully, it almost touches, the two essentially touch at some point. So in this case, it's not just weak duality, but strong duality also holds. All right? And that's something that we should expect, because in this example, the primal optimization problem was convex, and Slater's condition holds. Because I can find some point, so I take any point in the interior of A and B, it satisfies these constraints with strict inequality. Right? So Slater's condition is satisfied, the primal optimization problem is convex, so strong duality holds. All right?
What's the idea behind status condition?
It's just a technical condition, there's nothing else to it.
Like, why would that even matter?
Because we can come up with convex optimization problems which don't satisfy Slater's condition, and you don't have strong duality.
Like, why would having an X such that the constraint is strictly residence even sort of influence the dual optimization?
So again, it's generally some of these sort of, in some sense, pathological examples, but here is a concrete example that I'll for now give as a homework. Let's consider the following problem. All right, it's not a particularly interesting optimization problem, but nevertheless it's a problem where Slater's condition is not satisfied. All right. So in this case, the domain is not all of Rn or Rd, but it is the set of all, say, x1, x2, such that x2 is greater than 0. No constraints on x1, but x2 is greater than 0. This is the domain. Okay, this is where the objective function and the constraint functions are defined. And the problem is minimize e to the power minus x subject to the constraint that x square by y is less than or equal to 0.
x1 squared by x2 squared?
No, x square by x1 square by x2. That's it. Oops. So x1 square by x2 is less than or equal to 0. So first convince yourself that this is indeed a convex optimization problem. Now in this case, what is actually the constraint set? right? So these constraints, for what values can x1 take if it has to satisfy the constraints?
Can't you make it a multiplication?
Which multiplication?
x1 square into x2 plus the x2.
No, this is how I'm defining it. Okay? This is the optimization problem. You can't change this.
Both are not.
Which one?
x1 square by x2 and x1 square into x2
Okay.
less than equal to 0. Because you technically checking if x2 is negative.
By definition, the domain is x2 greater than 0. Again, I don't allow you to change this, because if you change the constraint, the constraint set may not change, but the dual optimization problem is going to change, right? Okay. So what values can x1 take if it has to satisfy the constraints? You can only take the value 0. Okay. And x2? X2 can be anything that is greater than 0. Okay. It seems kind of artificial over here, because the objective function depends only on x1. And this constraint, this x2 is sort of introduced to force x1 to take only one value. It can't take any other value. Okay. In this case, what is the minimum equal to? What is the solution equal to? Yeah. So P star is equal to 1 in this case. Okay. As I said, it's not a terribly interesting optimization problem to solve. But let's look at the dual.
So in order to prove it is a convex optimization problem, one is your objective function is convex.
Correct, that is
Two
obvious.
is the constraint set is convex.
Sure, all you have to
It's the
show.
point as you just shown.
No. So what you basically have to show is that x1 square by x2 is a convex function of x1, x2. Prove that.
X2 is the convex function of x, the vector x.
Correct. Prove that it's a convex function. That's it. And now construct the dual. x1, x2, lambda.
So just clarify. So it is not enough if the constraint set is convex, but each of the constraints should be a convex function. Is that what the
If each of the constraints functions is convex, then the constraint set is also convex.
okay,
Because in the end, we are describing everything in terms of these functions. The problem itself is defined using these functions. So whatever property you ascribe, it should be to these. Okay? Because I'm also demanding that if you have equality constraints, then these equality functions, the functions that define the equality constraints, must be affine. They can't be arbitrary convex functions. Okay, so what is the Lagrangian equal to? It's e to the power minus x1 plus lambda times x1 square by x2. Right? What is the infimum overall x1, x2, L of x1, x2, lambda? No, it's the entire domain. So x1, x2 in the domain, right? How will you go about trying to solve this? Okay.
Partial derivative.
Will you try doing that?
So should the constraints be convex over the entire domain or only the constraints?
Which one, sorry?
The constraints.
You mean the original primal problem? I didn't quite get the question.
You have
So the problem is of the form minimize f of x such that f1 of x is less than or equal to 0, where f and f1 are both convex.
if I have two constraints, let's say,
Okay?
the first constraint eliminates part of the domain.
Okay?
And is it sufficient if the second constraint is convex in the remaining domain, or should it be convex of the entire domain?
Whatever we are defining over, we have a common domain D where all of these functions are defined. So you fix that. You say that f, f1, f2, f3, all of these are defined on a common domain D, and over this entire D, we want x, we want f, f1, f2, f3, all of these to be convex.
And can we just say that x1 is like infinity and x2 is maybe infinity?
So what is the infimum equal to? So let's recall what we've seen previously. So one way of finding an unconstrained minimum or a local minimum is by taking the gradient and setting it equal to 0. Right? When is this guaranteed to be a local minimum? Or when does this approach generally works? Function is convex. Forget about convexity. Local minimum. Sorry? Again, let's go back to the question that I just asked. When is this guaranteed to be, or this? So if you just set gradient f equal to 0, under what conditions on x will you get this to be a local minimum? It is an interior point, right? So you can find, by setting the gradient to be equal to 0, you can find local minima that are interior points, right? So firstly, in this case, what you have to verify is there a point? When I say an interior point, it is the entire first region above x1 axis, x1. Yeah. So x2 greater than 0 is a minimum achieved at any interior point or not. You mean that may not happen, right? So the whole process of setting the derivative or the gradient to be equal to 0 and finding the solution to basically the first order necessary conditions works if you have an interior point that is a local minimum. In this case, there is no interior point which is a local minimum. Basically, the infimum is never achieved. My claim is that this infimum is equal to 0. So first, let's try to prove that the infimum is actually equal to 0. Okay, let's try to convince ourselves so that this is the correct answer. So first you agree that L of x1, x2, lambda is greater than or equal to 0 for all x1, x2 in the domain and lambda greater than 0. That's fine, right? So this is greater than or equal to 0. That's not a problem. So if I can show that the infimum is 0, then I'm done, right? Or infimum is less than or equal to 0, and then I'm done. Correct? Okay. So now let me set. Let's take x1 to be equal to some t and x2 to be equal to say t cube. Okay. I'm searching for the minimum of L of x1, x2 within a subset. Okay, it's a subset, it's a parametric set. So x1, x2 are of the form t comma t cube. It's an arbitrary choice, but the minimum overall t of this particular quantity may or may not give me the solution, but if the infimum of this overall t is equal to 0, then it must mean that the infimum of this overall x1, x2 should be equal to 0. I'm sorry? Huh. Try and if you get and see whether you get 0 or not. All right. The point that I'm trying to make is that infimum overall t greater than 0 of L of t cube lambda versus infimum overall x1 and x2 greater than 0
Lagrangian being positive or 0 is a claim, or
which one?
L x1 x2 lambda is greater than equal to 0?
This.
Yeah.
In this case, do you see that it's not true? So the domain x2 has to be greater than 0, right? And x1 square is non-negative. E to the power minus x1 is non-negative. Lambda is also non-negative. So this is greater than or equal to 0. All right. So now what can I say about this versus this? So, all right, because on the left hand side I'm minimizing over a smaller set of x1, x2. On the right hand side I'm minimizing over the entire domain. All right. So if there's some value and I know that this quantity is greater than or equal to 0. All right. So let me try to solve for this. What is it equal to? So what is L of t cube lambda? It is e to the minus t plus lambda times t square divided by t cube. So it is lambda times 1 over t. What is the infimum of this over all t greater than 0? It is 0 because e to the minus t is a decreasing function of t. 1 over t is also a decreasing function of t. So for every lambda greater than 0, the infimum is equal to 0. So the quantity that I'm interested in, this is greater than or equal to 0, but it's also less than or equal to 0. So it should be equal to 0. All right. So when it comes to computing the Lagrange dual function, you will encounter these sort of situations. Right? In many cases, you will not be able to get the minimizer or the Lagrange dual function just by taking the derivative and setting it equal to 0. This in many cases does not work because the infimum in many cases is not achieved. At some point at infinity, so these kind of scenarios occur very often. Okay, but in any case, I can get a closed form expression. Okay, so what is the end result? What can I say about g of lambda? Yeah? G of lambda is identically equal to 0 for all lambda. So what is the maximum over all lambda greater than 0 of g of lambda? Or what is d star? So d star is 0. But p star is equal to 1. Alright? The p star is equal to 1, but d star is equal to 0. So weak duality holds, but strong duality does not hold, even though the original problem was convex. Right. This is a simple example in two variables, but you can think of multivariable problems where such scenarios can occur. All right. So Slater's condition, again, it's a sufficient condition, but if it is not satisfied, then you can't guarantee strong duality. You may have only weak duality.
What is the status condition involved?
It basically, in some sense, involves the supporting hyperplane theorem. I'll see if it is possible. I'll try to give a proof, or at least point you to a reference. I believe the book by Boyd and Vandenberg has a proof that Slater's condition is sufficient to guarantee strong duality. Okay, so I'll stop with another sort of homework example. So this example is to illustrate that you can have strong duality even without convexity. All right. So consider the problem, minimize square root of x, where I'm only looking at the positive square root, subject to the constraint that 1 by x minus 1 is less than or equal to 0. So firstly, this is a non-convex. But what I also want you to do is do this with a slight modification, minimize square root of x subject to the constraint that x is greater than or equal to 1. Right? The point here is that this set of the set of all points that satisfy this constraint is equal to the set this, right? these two are effectively describing the same constraint set. But I want you to find the Lagrange dual for both of these separately.